Welcome. So we will see some of the engineering application of the fundamentals of integrals, and we will see how these very basic and very fundamental mathematical concept could be used in wide application related to engineering. Uh, you actually all these fundamental you use them in many applications that you do in the background, like you don't know that these concepts are used. Like for example, when you use CAD, like AutoCAD software or GIS, uh, to calculate areas, volume, this is all based on these mathematical concepts. So here today, or in this video, I will show you how these mathematical concepts can help you to evaluate models, so to evaluate different model performance and be able to select which are like the good models that you can proceed with. Yeah. Let me show you this case study. I will show you the case study, and then first I will introduce the case study first, and I will then show you how this uh, uh, integrals or these things that we learn about integral calculus helpful in these applications. Okay, so here we have this is called the Southern Hill Aquifer. It's shared by several states, including Louisiana. So this is Baton Rouge, Louisiana capital. For example, you have like a fault here. These are different aquifer unit on the subsurface, as you see, like it's like cakes, like a layer. So this is an aquifer, aquitar, like no, like permeable layer, aquifer, and so on. And you see, due to over pumping, here's saline water, here's fresh water, and due to over pumping, you start to have salt water intrusion problem across this fault where saline water is intruding and salinizing basically fresh water. Yeah, and so how to solve these problems? So to solve this problem, we create like a flow model and density dependent model or flow model and transport model, something that can transport like chloride or something like this. And then you use this model to make your design, your engineering design to mitigate this problem, which, for example, one design would be to relocate pumping because saltwater intrusion happens through preferential pathway. So you can relocate your pumping station. So most of the pumping is occurring here in this industrial district, but some of the pumping is also occurring in for municipal use. Other engineered applications, engineered design would be to pump and treat, like pump, like you pump the water out, the saline water out. Other application would be to create like a hydraulic barrier. So you put an injection well and pumping well, and this will circulate the water and create like a hydraulic barrier. But for any of these application, I will show you one of this application by the end of this video. You need flow and transport model or a density dependent model. Okay, so here, this is one model that was developed. This is the solution of this model where it's based on mud flow. So mud flow was used to simulate the flow. MT3DMS was used to simulate the transport, chloride transport. And what we like, you see here, this is the saline water, this is the fresh water, and we will project this for 100 years. So if we projected this for the 100 years, so this is where the plume, the current saline plume is, and let's see 100-year projection. So a 100-year projection, it shows that our saline water will go to Entergy. So you have like two energy company, ExxonMobil and Entergy, like um, municipality, and basically the one who will attract the saline plume and will have like saline water will be like the Entergy, and the ExxonMobil wells are okay. Yeah. Uh, Now, so we developed this model, yeah, and so we developed this model. Another group were working on the same problem, and they developed this model, and their model simulation shows that by the same time period, this saline plume will not be attracted to Entergy, but will be attracted to ExxonMobil. So the salinization will occur here and not here. So now the question is, which model should we believe? Like if we want to build a design, which which model should we use? Like the ones that tell us that the saline plume will go to ExxonMobil, or the ones that tell us that will go to Entergy? How could we select between these two models to build our design? Yeah. So it could be the both models are wrong. Yeah. Maybe none of them are wrong, or maybe one of them is true and one of them is wrong, but we don't know which one. So how can we do this? So actually, it is not. This is like which model is right and which model is wrong. This is not the right question to ask. The right question to ask is which of these model is more scientifically defensible. So the one that's more scientifically defensible, this is the one that I can base my design on, while uh, I have like justification for what I'm doing and for the designs that I'm having. So to have a scientifically defensible model, there are certain things that these model, certain features that these model have versus this one does not have. Among these feature, I mean, I will not go into details, but among this feature is that this model is a simple model and high fidelity model. Simple model means that it has only very few parameters. High fidelity means that's very realistic with respect to the subsurface. So allow me to show you. So here, this is an example of a low fidelity geological model, but complex flow model. Why low fidelity? Because the subsurface does not look like this. It does not look like these sharp zones. Subsurface would more likely look like this, like smooth transition. So this is low fidelity because it's not realistic with respect to how the subsurface looks like. This is high fidelity with respect to how the subsurface looks like. This one is complex model. Why? Because it has many parameters. So I make this zone, I make this zone, I make this zone, and then for each one I will estimate a hydraulic conductivity value. Because you see here, this looks different than this guy and looks different than this guy. So I will estimate a value here, I will estimate a value here, I will estimate a value here. I will see this guy looks different, so I'll estimate a value here, another here, another here, and so on and so forth. Yeah, so this will end up by having 15 parameter. This will only have 3 parameter because I only have 3 phases. I will estimate one value here, one value and here, and one value here. So now I need to, so this is called like low fidelity complex flow model because it has many parameter. This is called high fidelity because this looks more realistic, and simple flow model because it only has 3 parameters. So now I need a metric that will uh, reward both of these models for being able to reproduce what we are observing in the field, because you develop a model, that's easy, but to make your model realistic, that means a calibrated model, a model that's able to reproduce what you are observing in the field, that's not easy, that's more challenging. So I want to have a metric. This metric, if the model can reproduce what I am observing in the field, it will reward it for this. But I want this metric also to penalize the model. If this model has more parameter, it should be penalized for this. Because if I have a lot of parameter, I can basically fit anything and reproduce anything. This is called overfitting. Um, so I want to avoid overfitting, that is like to reward the model for reproducing what I'm observing in the field, but to penalize the model if it is complex, if it has so many parameters. And how can we get this matrix? Well, this matrix I will show you after this, like after I introduce the case study, how you can develop this matrix and solve it based on these things that we learned from calculus, integral calculus. Yeah. So we develop a model. So that would these are the different layers that I showed you, like in the subsurface. Here's the Mississippi River, for example. Some of you asked me in the introduction, like, what are some of the models that you develop? So these are some example of the models that I developed for saltwater intrusion management, for example. But this is just one image. This is just one image of the subsurface. So, like, to make your model scientifically defensible, remember I told you rule number one is what? Make the model high fidelity. Rule number two is what? Make the model simple. Rule number three is what? Is that you should have multiple working hypotheses, because this is just one image, one conceptualization of the subsurface, but I could have different conceptualization for my subsurface. So here is an example. Like these layers here have like dipping angle. We don't know these dipping angle, so we can estimate these dipping angle from the data we have. So here we have two methods. We use like two, actually, machine learning type of method to estimate like the dipping angle. So now we have two method for estimating dipping angle. Like, which one are you going to choose? Yeah, so this is just one source of uncertainty, conceptual uncertainty. What are other sort of uncertainty? What is the method, like geostatistical method? So you have geophysical data. So you see here, like this borehole logs, this give you the hydrogeological and geophysical data, and then you use this data to create this image. But which method are you going to use to create this image? So you can use something like indicator zonation, you can use something like generalized parameterization, and you could use something like indicator kriging. So here, we are not only uncertain about the dipping angle, but we are uncertain about the geostatistical methods, the methods that we use to characterize like the subsurface. So here we tried like three of them: indicator zonation, generalized parameterization, and indicator kriging. And you see how like the subsurface, like I'm just showing one layer on the subsurface. The white is sand, the black is clay, and you see sand means like where you have flow is occurring. So you see here flow, this is the fault. Flow will occur here, 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 and like here. Versus this one, flow will occur here, here, and will get some trapped here, and some of it will go here. Versus this one, flow will occur like this one flow. But you see, like there are different images, yeah. So now this will end up with 6 models, 2 for different dipping angle, and for each one you have 3 geostatistical method. Okay. What are our other sources of uncertainty? We could be uncertain about the boundary condition. Like here, for example, we don't know this boundary condition. So we can create this boundary condition using this group of wells. See this cluster of well? We call this E1, like eastern boundary condition number 1. Or we could create our boundary condition using this cluster of well. We call this E2. So E2 is based on EP297, like this guy. EB like East Baton Rouge 297, and this guy is based on like this cluster of well. But which one to choose? We don't know. Now, what are other sort of uncertainty? We are uncertain about this boundary condition. Like this boundary condition is the opposite of this one. Like here we have too many data. Here we only have very few data. So we only have, this is EP904, which is this guy. We only have for this guy 2 points. 2 points in 1985, 1 point in 1985, and another point in 1990s. That's all. That's all the hydraulic heads that we have for this guy. And then for another one, like this guy here, we only have another 2 point. So what can we do? Like the simplest thing you can do, you can just assume straight line here, you connect straight line here, you connect straight line here, and you just connect straight line here. That's the simplest thing you do. Another thing you do, we have continuous data for this guy, 305, so we can get this guy and adjust it to this head data here, and then you'll get something that looks like this. Okay, so for this boundary condition, we have two uncertainty, like either we use like N1 preposition or N2. We don't know which one. And here we could use like E1 or E2. So if you have like here, so remember from the geology, we had 6 model. From the flow, we have another 2. So 6 times 2, that's 12 model. And here, and from this one, another 2, that's like 24 models. Okay, so now we have 24 model. So this is uh, third condition for making your model more scientifically defensible is that you have multiple working hypotheses. You don't only assume one thing and you work with it, but you acknowledge all your sources of uncertainty and you try to account for these sources of uncertainty. So now we have 24 model. What are you going to do with them? That's very difficult to deal with 24 model. And that is where we need to do some sort of screening for these model. And what is this screening? Remember, I want to reward these model if they have good performance, and I want to penalize them if they have more parameters. That's basically the screening, and that's when the fourth condition, which is the strength of the evidence. So basically, like you calibrate this model. This is what we did here. So this is like an example, one of these model getting calibrated. So this model, for example, has 6 parameters to calibrate. So this parameter include like one hydraulic conductivity value, one isotropic value, one specific storage value, 2 conductance value, one at this fault and one at this fault, and one here like a tuning parameter for my boundary condition. And you see, like here's the calibration is very good calibration. So like the blue lines, this is the model simulation, and these black dots are the field observation. So you see here, for example, like in this guy, remember this guy here, we only have 2 dots. See what our model is simulating just perfectly fit with this guy, perfectly fit. So you see a very good match between what the model is simulating and what we are observing in the field. So this model should be rewarded for doing a good job. But other model, like because they have like not good modeling idea, because we don't know which ideas of these 4 ideas that I showed you, like of which of these propositions that I showed you before for this different uncertainty is good. But once you give it a metric like this, then this metric will help you to get rid of the bad idea. So let's look at the output of this, for example. So this is the head simulation. This is the eastern boundary condition. See, that one didn't contribute much to the uncertainty. The northern boundary condition that contributed a lot to the uncertainty. The formation dip that contributed some to the uncertainty here, and the geostatistic methods that contributed most to our uncertainty. But how did we know this? Like, how did we know that this is how much uncertainty this guy did? This is how much uncertainty this guy did. This is how much uncertainty this guy did. Again, we knew this because we were able to calculate something called the Bayesian model evidence, which would reward the model for its good performance and penalize it for its bad performance. So here, with respect to the eastern boundary condition, you see eastern boundary condition number 2, like this second proposition, it all got 0, 0, 0, 0, which means that this is a bad idea, basically. Now, the northern boundary condition, which is here, like this one, both of them got equal score, which means both of them are good ideas. But so you see here is their score were like 50-50. Yeah, so both of them are good idea. With respect to the formation dip, so under the formation dip 1 and under formation dip 2, see this one got higher scores than this guy got higher probabilities than this guy, and this guy got higher probabilities than this guy, which means that this tend to be like a better idea than these guys. And then with respect to our construction, hydrophases construction method, like the 3 geostatistical methods, this one almost got 0 probability, 40% and 50%. So these are 2 good ideas. So based on what we have learned, now we can just like eliminate the bad idea. So for sure we need to eliminate all these guys because these are bad idea. We look at here, this is 50-50, but they contributed uncertainty to areas that we are not interested in. Like we are interested in simulating the flow and saltwater intrusion here, not beyond this fault. So basically these 2 are like both of them are good idea. You can just select any of them. So I will just select N2 because generally speaking, under different proposition, it got higher weight. So you see now I was able to get my 12 model to reduce them to 6 model. Now I look at these 6 model. Now this one, you see here, has almost 0 probabilities as zonation. And we know that this is like, in advance, we know that this is a bad geostatistical method, but we just wanted to try it because this is zonation. We know that the subsurface is not sharp zone. It will be either like this guy or this guy. So we can get rid of this guy. And now we ended up with only 4 models. So like 2 geostatistical method, and under these 2 geostatistical method, we have 2 dipping angle, like dipping angle number 1 and dipping angle number 2. You see this guy got like low probability, so you can get rid of this guy. We ended up with only 2 from models. So you see, so now this is the fourth. So remember like how to make your model scientifically defensible. First, simple model or high fidelity model. Second, simple model. Third, multiple working hypotheses, like you acknowledge your uncertainty and you test your different sources of uncertainty. Number 4, strengths of the evidence, like for all these model, like rewards the model for being able to reproduce the field data and penalize it for being more complex, more parameters. So that's number 4. Number 5 is equifinality, like we were able to get rid of all the bad idea and ended up with like only these 2 models. So equifinality, when more than one model can plausibly fit the observation data. So these 2 models can plausibly reproduce our observation data. So what can we do? We can just like use these 2 models. Like when you make a design, make your design using these 2 models. That's one way. Or collect more data until you were able to get rid of one of them, and then one model just is fitting your data more. Yeah. So now let me just before I tell you like, but what does this has to do with integral calculus? Before I answer this question, what does this has to do with integral calculus that we learned? Let me just show you the output of these models. So here, so the output of this model. So this is our model simulation is telling you that. So this how much this company is pumping. 8 million gallon a day. They have 7 well, and these are the companies that attract this plume. So if you want like to design this, like one way you can relocate this pumping station. So if we relocated Baton Rouge Water Company pumping station, like move this guy, it's not going to affect anything because this is the guy who's attracting the plume. If we relocated ExxonMobil pumping station, it's not going to affect anything. So this is a simulation where we are relocating this guy. But if we relocated this guy, so this guy moves their pumping well, that will mitigate the problem to a certain extent. Yeah. Okay, so that's like a toy. Like now you have a toy to play with, and then you can run this model, and you can do different designs. As I told you, hydraulic barrier, pump, and trees. They call it scavenger wells, or whatever you want to do. Yeah. Simplest solution for this would be just to reduce your pumping, but that's something else. Okay, so now what does this has to do with integral calculus that we learned? Okay, let me show you what does this has to do with integral calculus that we learned. So just let me give you, so basically this has to do with integral calculus because remember I told you you have to calculate the strengths of the evidence. That's to reward the model for reproducing the field observation and to penalize it for being complex. We did this actually using something called thermodynamic integration, which is based on this integral calculus that we learned, which I will show you in a minute. But before we do this, let me just give you some background. So moments summarizes the distribution properties such as mean, expectation, variance, skewness, and kurtosis of your probability density function. So all these models that I've showed you previously, one thing I didn't tell you about these models, these are not deterministic model. So like, remember I told you have 24 model. Each of these 24 model is a probabilistic model. It's based on a probability distribution for your parameter. So your parameter, when we do model calibration and we estimate parameter, we don't just estimate one value, we estimate a distribution basically. Because we know that like this parameter is not just one value, it's a distribution. Like my hydraulic conductivity, yeah, let's say it's like 10 to the power minus 3. Yeah, but it could be here maybe 10 to the power like minus 4 or 10 to the power minus 2. Yeah. So it's a distribution, yeah. So we estimate a distribution for for each of these parameters. So you see here, does this look familiar? So here, the expectation of a function, like, so this is like my probability distribution, like random variable. So that could be any random variable. That could be my hydraulic conductivity. That could be the fault conductance. That could be the specific storage. That could be the whatever, yeah, the anisotropy ratio. So the expectation of any of this variable, expectation means like the expected value, the mean value, that is, you integrate this value over from negative infinity to positive infinity, so like full domain. So that's like your x to the power k f of x dx, yeah. So for example, the first would like, so this is called moments of your distribution. So the first moment measures the average value of my distribution x, like the mean value. So it tells you like, what is this guy? Remember, I told you like you can use integration to find like the area under the curve or the mean value or whatever. So basically the first moment measures the average value. So you integrate from negative infinity to infinity of like this guy here, where xk is equal to is power 1. And then if you did this integration, you'll get the mean value. The second moment, where k is equal to 2, we call this the second moment. It measures the variance. The variance is the spread, like how spread this guy is. So here you see this guy is spread versus like, see, this guy is not very spread, like it's narrow, something like this. So that's the variance. It tells you like how much the spread of this guy here. The third central moment give you information about the asymmetry, like the distribution, skewness, like, so here, like your distribution could be, so this is like a normal distribution. This is like skewed to the left, and this is like skewed. My handwriting is not good. And this is like skewed to the right. Yeah, it's like skewed to the left, and this is skewed to the right. Your fourth central moment, where k to the power 4, that gives you about like the peakness or sharpness of your distribution. So let me show you here an example. So, for example, this distribution is just at the center. This distribution is skewed to the left. This distribution is skewed to the right. Here, this is the Cortosius, like your force moment of your function, and that basically, if it is 0, if like this if this beta for, I mean, I'm not showing you the equation for this guy, but if this beta, for example, beta value here is 0, you got like a normal distribution. If it is -1, you get a uniform distribution. If it is +1, you get this Laplace distribution. Yeah, so that's how this equation here, like, so from integral calculus, this basically will tell you, like, can tell you something about the shape. It can tell you something. This equation here, this Q, will tell you it's like to the right or to the left and so on. Okay, but so let me now, so this just to give you some basic terminology about like the moments of a function. If you don't understand much of what I'm saying, that's fine. I mean, don't worry. I mean, these are advanced material, and just try to, whatever you can understand, whatever you're not understanding, that's fine, because all these are advanced material, and I don't really expect you to understand much of it, but at least you just get an idea. Yeah, you get, at least you know what is the skewness, what is kurtosis, yeah, and what is variance, what is mean, how my distribution could be skewed to the left, how my distribution could be skewed to the right. I mean, that's as much as you just get some flavor of it, basically. So now let's get, remember I told you I need a matrix. I need a matrix that will penalize. I need a matrix. This matrix will penalize my model. It will reward my model if it can reproduce the field data. Good. But it will penalize my model if it is complex. Yeah, if it's a complex model. This is the matrix. So basically, this is my posterior probability. This is the likelihood. This is my prior knowledge, and this is the Bayesian model evidence. So let me walk you through this. So what does this mean? Yeah. So what does this mean? This is the most important one. This is the likelihood. So basically, this is telling you what is the probability. Yeah. This is telling you what is the probability that this model giving this parameter will reproduce this data that we are observing in the field. Yeah. So here, this is what this guy is. What this guy is our prior knowledge about this model. So basically, this is our prior knowledge, our prior like what was how this model is like reproducing like this parameters that we are observing. Yeah, so this is our prior knowledge about the model. This is our posterior knowledge about the model. So like let's say for example I have a prior knowledge about a student. Yeah, and then I give the student an exam. Yeah, so and then I see the likelihood is basically how good or bad he will perform in the exam, and based on my prior on the exam result, I will update my prior knowledge to a posterior knowledge. So my posterior knowledge will be like a mix of my prior knowledge. My prior knowledge will not fade completely, but what we learned from here will like be big part of the equation. But now, if this student was like, let's say, giving more resources, like let's say this student has like 15 resources versus another student who only has 3 resources. So that needs to be taken into account. And this is the Bayesian model evidence. So, and that is where, so resources here, like this model has so many parameters, many degrees of freedom, it can fit anything, versus this model has only few parameters and is very restricted. And so if it's very few parameter you play with and the model is fitting already what you are observing in a field, this means a very good model. So what is this guy? Oh, now here's the problem. This is the problem, and this is where, so this guy basically I am integrating all my likelihood, yeah, over all my, and my likelihood time my prior knowledge over all my parameter space. Oh my god. How do I do this? What is my parameter space? Remember in the previous models that I just showed you, the parameter space, it has like 6 parameters. So this model has like 6 parameters, and each parameter, like say hydraulic conductivity, that could be go from like let's say 10 to the power minus 5 to 10 to the power minus 2, for example. Specific storage goes from 10 to the power minus 6. I'm just making these numbers up, yeah, to 10 to the power minus 5 or whatever. Yeah, I'm just making these numbers up. So each of these parameters, this is basically the, so like if I will form this problem, that would be like, remember this was 6 parameters, 6 of them. So I will have like 6 of these guys, 1, 2, 3, 4, 5, 6. Yeah. And each of these guy will, like, let's say the hydraulic conductivity, that would be from 10 to the power minus 5 to 10 to the power minus 2. That will be like delta K. This would be like the specific storage, 10 to the power minus 6 to 10 to the power minus 5. This is basically what this integral is, but which we can also write it as, remember, R is equal to 6. But that's very difficult to solve. And this model only has 6 parameters. What if the model has 40 parameters or whatever? So that model is very difficult. Like this integration is very difficult to solve. So let me show you like here, and if you see like this article that I showed you here, basically in this article, we came up with a method. So let me show you. So this is the integral that we want to solve here, this guy. Where can I do this? Yeah, I think we can here. So this is like the guy that we want to solve. We want to solve this guy, but this is a multi-dimensional integral. To be 6 dimension, like in the previous case studies that I showed, that would be 6, and some model might have like 6 parameters or whatever. So it's not easy to solve, yeah. So how can we do? So like if you go here, like you can read this derivation. So basically this is Laplace approximation. This is the thermodynamic integration. So like if you read this derivation, I'm not going to go through this, like not to make the video long, but you can go on it on your own. you will see some of the concepts that we learned, like integration by part and like some of these rules of integration and integral calculus. You will see them, how we applied them here in order to convert like this multi-dimension integral that you see here. You see this multi-dimensional integral, to convert it. So you can look at these like laws of calculus, integral calculus. You can look at this derivation until we just ended up to be something like this here. This is a 1D integral. Let me clip this for you. So you see here, this guy, I converted my 6-dimension or whatever multi-dimension integral to only a 1D integral. See, this is just 1D integral. And the approximate solution for this guy is this, because I'm solving it numerically. I'm not going to solve it analytically, so this has no analytical solution, so you can just solve it numerically, and then once you solve it numerically, that would be the numerical solution. So we're not going to talk about numerical solution in this module, and I think when we get to the modeling part, that's when we will talk about integral we will talk about a numerical solution, yeah, and how to solve something like this numerically. Actually, solving this guy, it looks scary, like mathematically speaking, but solving this guy numerically is trivial. And I will show you. But that's the idea, yeah. So that's like the idea. You can look at this derivation and see how like different tricks from integral and differential calculus like was used here to come up with to convert this multi-dimensional integral to this single to only one dimension integral, which make it much easier to solve. Okay. So this is just some engineering application of what we've been doing of this like integral calculus and transforming multi-dimensional integral to one-dimensional integral to estimate Bayesian model evidence. In your field and in your career, I don't know how you're gonna apply this. So I want you to, for example, like in the exit ticket, you can answer, you can tell me like how could you apply this in integral calculus in your through like your job or in your career, or if you don't know yet and you still need until we get to differential equation and get more into the course, you can just answer this question. Like you asking me question, what model did I develop? So I just saw you like some of the one I showed you so far, like several. One I showed you the ones that we use for remediation to design a remediation system, and this one for saltwater intrusion management. I want you to tell me like what models did you develop or are you developing in your job, uh, and uh, and what metric do you use to evaluate these model? Like how would you select which model is good or which model is bad, or how what method do you use to calibrate and post like evaluate these models? So you can answer this question, uh, uh, or if you cannot answer any of these two questions, uh, you can just like make it the regular exit ticket. Okay, so that is all for this lesson here. This is, if you want to read more about the case studies that I just showed you, you can read about more it here, like Bayesian model evidence. You can read about it more here. And